Hi guys, in this video we shall be looking at conservation of linear momentum. But before we talk about conservation of linear momentum, let us look at collision. What is collision? Collision is when two or more objects come into contact with enough force to either damage them or impede their progress. So we have to measure the two types of collision. We have elastic collision and inelastic collision. So you have elastic and inelastic collision. So how can we picture this elastic collision? So you have two bodies represented in this picture. So this is body A, this is body A, and this is body B. You see that when these bodies are in motion, so this is body A with this mass MA, and the velocity is moving with is UA. Of course, the initial velocity here is not zero because they are in motion. So when these two bodies collide, of course this one is more massive than this, but on collision you see that they will move with different velocity. So this type of collision is known as elastic collision. In elastic collision, as we shall see, both the momentum and kinetic energy is conserved. So we notice conservation of momentum before and after collision, and conservation of kinetic energy before and afterwards collision for a perfectly elastic collision. So another example of this elastic collision is collision of billiard balls and collision of molecules and atoms. Another one is a tennis ball that bounces back to its original height after hitting a surface. Okay, so we say that this surface is having elastic collision with the ball. So these are examples of bodies having elastic collision, and as I've said, both kinetic energy and momentum is conserved for elastic collision, as we shall see. Now for inelastic collision, we have only conservation of momentum. The kinetic energy is usually lost either due to heat, okay, coming as a result of friction or external force. Okay, so you see that kinetic energy is lost in inelastic collision, but momentum is conserved for a body in an isolated system where there is no external force. So we notice that momentum before collision will be the same as momentum after collision for an inelastic bodies in an inelastic collision, but the kinetic energy is always lost. So we shall demonstrate that in this lecture. So you notice that for these two bodies now, let's say this is a ball is moving and you have another stationary ball. Of course, as this is stationary, the initial velocity will be zero, this will not be zero. So you notice that when these two bodies collide, this is more massive than this. They can collide and move in the same direction. So if this one is to be more massive than this, they can collide and move in an opposite direction. So in this type of collision where two bodies collide and move with the same velocity, you call that inelastic collision. Inelastic collision. So let us look at conservation of momentum for bodies that are in elastic and inelastic collisions. If this is your first time of watching this video, give it a like and subscribe for updates like this. We upload videos on science and technology and on of course sciences and technology, and this is an educational channel, so you can invite your friends. Subscribe, locate the subscription button below, it is free. Subscribe for more video updates like this. So let us look at conservation of momentum for elastic collisions. So conservation of linear momentum. Conservation of linear momentum. Momentum is a product of mass and velocity. So we say that momentum is conserved in an isolated system, that is a system where there is no net external force. So if two bodies are moving in an opposite direction and collides, in an isolated system, momentum is said to be conserved. So let this be body A, so that this body A will have mass ma, and this body B will have mass mb. So if this is moving with initial velocity ua and this is moving with initial velocity ub, so we can write expression for the conservation of momentum here. So we shall do that following Newton's third law of motion, which says that action and reaction are equal and opposite. So on collision, if these two bodies are now to collide, on collision, you notice that the force on A will be equal and opposite to the force on B from Newton's third law of motion. And we know again that from Newton's second law of motion that force is ma, which is this. Of course, acceleration is change in velocity with respect to time, so we have it as this. If we now employ this Newton's second law and Newton's third law, we can come up with an expression for the conservation of linear momentum for bodies in elastic or inelastic collisions. So we look at Fa. So utilizing this, we have it as, let's write this first. This is Fa equals minus what? Fb. So this will be ma Va minus Ua upon T. The time will be the same, equals minus mb Vb minus Ub upon T. So if we multiply both sides by T, you notice that this goes, the time is same. So if we multiply through, you see that this is ma Va minus ma Ua equals, this will go through this, have minus mb Vb minus minus, this is multiplying, this is plus mb Ub. So you notice that when you rearrange this, this will come over here. You have MAVA plus MBVB. This will go over there. You have MBUB plus MAUA, which we can as well write as this. We can write it as this MAUA. That is writing this one first, plus MBUB, that is this right hand side, I've written it first, equals MA, this is MAVA plus MBVB. So this is the equation that shows conservation of linear momentum for bodies in elastic collision, bodies in elastic collision, bodies in elastic collision. You see that the final velocity after the collision, this is momentum. I will label it with pi to show momentum, initial momentum before collision. This is pi and this is final momentum. So notice that momentum, initial momentum before collision equals final momentum for bodies in isolated system. You notice that the velocities of the bodies are different. You notice that VA is not equal to what? VB. So the two bodies collided and moved with different velocities. Now let us look at now conservation of kinetic energy. Kinetic energy is the product of mass and velocity, and following from this equation we have, so the kinetic energy conservation of kinetic energy will be, so following from this we have it as half ma ua square plus, this is half mb ub square equals, you have half MAVA square plus half MBVB square. So this is the equation for the conservation of kinetic energy for elastic collision. So this is conservation of kinetic energy, and this is conservation of momentum. So these two formula, they are very important. The formulae, they are very important. This is for conservation of kinetic energy, and this is the conservation of momentum. You notice that in each of them, the final velocities are different. So let us look at conservation of linear momentum for inelastic collision. So for inelastic collision, we notice that the velocities after the collision will be the same. So the two bodies will collide and move with the same velocity. So let us write this together so that we'll be able to differentiate it. So for elastic collision, we have this as, for conservation of momentum, this is momentum, I'll write it as P. For conservation of momentum, we'll have it as MA UA plus MB, I'm writing this again, MBUB equals MAVA plus MBVB. So since the velocities are same for inelastic collision, so our equations for conservation of momentum in inelastic collision will be, so this is for elastic collision, so I'll write it as elastic collision. So for inelastic collision, it will be, for conservation of momentum, we have it as conservation of momentum, we have it as this, you have it as MAUA plus MBUB equals, since it will collide and move with the same velocity, this becomes MA plus MB to the bracket of V. So you see that the V is common. It implies here that VA equals VB. So you factor out one of the V's. So this is conservation of momentum for inelastic collision. So for inelastic collision. So for inelastic collision, we notice that kinetic energy is lost. So you have it as this, half MA/UA square plus half MB/UB square equals half MA plus MB/V square. So this is kinetic energy before the collision, and this is kinetic energy after the collision. So you notice that for inelastic collision, the kinetic energy before and after the collision is different. So kinetic energy is lost here. Kinetic energy is usually lost for bodies in inelastic collision. So as I've said, if this video interests you, subscribe for more video updates like this. You can check through our playlist for videos we have done on physics and mathematics, and as I've said, we will also upload video on other aspects of science and technology. So let us look at example problems. The question says a 4 kg ball moving at 8 meters per second collides with a stationary ball of mass. This is the mass is 12 kg, and they stick together. Calculate their final velocity and the kinetic energy loss. So when these two bodies collide and stick together, they move with a common velocity. So let us draw the ball. So this is, which one is more massive? This is more massive. So you notice that this is one of the balls. So this is 4 kg ball, is moving with velocity of 8 meters per second and collides with this ball that is 12 kg. Okay, and they stick together. So this is stationary. So we say collides with a stationary ball of mass. So this is stationary. Of course, the initial velocity here will be 0. So if this is to hit this, of course you know that it will collide and move with and move together. So it can move slightly forward because this is more massive than this. So on collision, if this is done in an isolated system, you notice that momentum will be conserved, but the kinetic energy will be lost. So we still make use of our formula. This is ma ua plus mb ub equals ma plus mb auto brackets v, because when they collide they move with same what velocity. The two bodies, when they collide, they move the same velocity. So this now will become, this is the mass of body A, so this is the initial velocity of body B, body A, so this is initial velocity of body B, this is mass of what, body B. So using this formula, we now have that MA is 4 times UA is, the UA is 8 meter per second. So you have 8 plus MB is 12 times UB. Since this ball is stationary, so this is 0 equals MA is 4 plus MB is 12 to the bracket of V. So this goes, so 4 times 8 is, so 4 times 8 is 32, and this is 4 plus this is 16. This is 16V. So if you make V subject of the formula, this will be 32 upon 16, and this gives us 2 meter per second. So the common velocity with which the balls move together with is 2 meter per second. Now let us see how the kinetic energy is lost for this collision. So for these same two bodies, so for to show that the kinetic energy is lost, that is, the kinetic energy before will not be the same as after. So using this formula, half ma ua square plus half mb ub square equals half ma plus mb, you have v square. You notice that this one is 0 because ub is 0. So the common velocity we shall be using is this 2 meter per second. So if that is the case, our formula condenses to half ma ua square equals half ma plus mb v square. So this will be the kinetic energy. This will be the kinetic energy before the collision, and this will be the kinetic energy after the what, collision, after the collision. So let us now solve and see if the kinetic energies will be the same. So if we solve the kinetic energy before the collision, kinetic energy before, so before is this, half MAUA square. So you have that this is half MA is 4 times UA. UA is 8 square. This becomes, this can cancel this. You have 2 times 8. 8 raised to the power of 2 is 64. So if we multiply this, we have 128 joule. So the kinetic energy before is 128 joule. So I write it here as this is 128 joule. So let's now find kinetic energy after. Kinetic energy after the collision. So I write kinetic energy after the collision. So this is the kinetic energy after the collision. So I have half ma plus mb all to v square. half MA still remains 4 plus MB is 12, and the common velocity we got is 2. So let's say 2 square. This is half 4 plus 12 is this is 16 times 2 square is 4. So this can go into this. You have 8. So 8 times 4 is 32. So now notice that the kinetic 32 joules. So you notice that kinetic energy after the collision is 32. Actually, kinetic energy was lost. So this is 32 joule. And to find the kinetic energy that is lost, the kinetic energy that was lost, you take the difference. 128 minus 32 is 96 joule. So this is one example problem on this momentum conservation. This is for inelastic collision. So if you have actually enjoyed this video, do well to give it a like and subscribe for more video updates. We shall be solving more problems on this. In our next topic, we'll look at collision in 2 dimensions, and we'll look at conservation of momentum in this collision. So have a wonderful day ahead.